Hello everyone, this is Dr. Caleb Chen again, and we want to be looking at the central limit theorem, and this would be a management application and utilizing the central limit theorem, and with the parameters given to us. In this case, what we're looking at let's say the soda bottles, 32 ounces bottles, and the target mean average is 32 ounces. Basically, it's 32 ounces bottles of soda, and you don't want to overfill it, neither do you want to underfill it. But there's going to be some discrepancy, and per the specification, we have a standard deviation of 1 ounce. So 1 ounce versus 32, and daily the production manager would take 25 soda bottles and examine how much soda has been filled into those bottles to determine if, say, the process has been working properly, so that we're not having any overfilling or underfilling problems. So in this case, we have framed the probability question. What's the probability when a sample of 25 bottles is taken, and that 25 bottles would give us a sample mean of greater than or equal to 32.5 ounces. So that's the problem, and we have every single piece of data or information that we need to calculate the probability. And notice in this probability statement is no longer x but x bar, because we're looking at the sampling distribution of sample mean, and we assume that we have a normal probability distribution, even though n is not quite 30, but let's assume that the population is normally distributed. So how do we approach that? I would first of all turn, say, some parameters around, so the mu x bar, according to the central limit theorem, is the same as mu, which is equal to 32. So that doesn't change. But the standard deviation of x bar is equal to standard deviation divided by square root of n. So given that sigma is equal to 1 and the square root of, say, 25, so that would be 1 over 5, or is equal to 0.2. So in this case, we have a standard error, which is also the standard deviation of sample mean, is also called standard error, versus the mean of the sample mean, which is the same as the mean of the population. So with these two parameters, let's sketch that normal curve, and this x bar distribution here is the center, which is 32. What is the probability that this would be 32 and a half or more? X bar is greater than or equal to 32 and a half or more. So this is the shaded area that we are concerned about. For us to compute this, the best way is to find out what is this piece from 32 to 32 and a half translate into. So the one thing that we can do is to determine since is the sampling distribution of sample mean. Let's add the standard error, which is 0.2 here, 0.2, and then we have right here x bar value. Let's also add the z value. 32 is the same as 0, and 32 and a half, we are using the equation z, and this sign for sampling distribution slightly different from previously. It's going to be x bar is x minus mu of x bar divided by sigma over square root of n. So in this case, the 32 and a half would be 32 and a half minus 32 divided by 0.2. So that would be equal to 0.5 divided by 0.2. So if my math is correct, it's 2 and a half. So this would be 2 and a half standard deviations above the mean, and that would give us from 0 to 2 and a half. If we go to the normal table again, 2.5 would give me 0.4938. So this is 0.4938. Well, we're only one step away from the answer. If say from the 0 to 2.5, it is 0.4938. The difference between say the 0.5 and this piece would give us the answer. Well, graphically, we probably should not have drawn a lot more here, because 32.5 would be 2.5 standard deviations away. So going back to the question, the answer in this case would be is 0.5 minus 0.4928, which is 0.0062. So there's less than 1% chance that we're going to have an X bar greater than 32.5 ounces. So in this application, we're talking about if say the production manager samples 25 soda bottles a day, and if the specification has been 32 ounces with a standard deviation of 1, which becomes a standard error of 0.2, well, we are going to have a very, very small chance that the X bar value would be 32.5. From the management standpoint, if say that the production worker who is doing the sampling, or might be the assistant the quality manager is doing sampling, and found that is 32.5 ounce, well, it is good enough information to allow say the management to say that might be the process is not working properly, and perhaps the half ounce is going to push say the bottle to be the bursting out, and someone opens the bottle and the soda is going to be the burst out, and that is undesirable. So that we want to take note of that. So this is one way we can use the synonym theorem, and based on the understanding that we have a normal probability of the sample mean when it's large enough, when n is large enough, or when the population itself is normally distributed. In many of the manufacturing settings, it can be assumed, because oftentimes we are dealing with the large number of products that are coming out of the assembly line. So hopefully this helps you, and we have to keep in mind that the same calculation would be used using the normal curve, just like we did in the previous chapter, chapter 7.